Welcome back. We left last time in the middle of a derivation, right? And the derivation had to do with establishing potentials. And the analogy is energy, potential energy, but it's much more abstract. Don't try to put too many units of measure there. In fact, sometimes don't even try to measure what we mean by a potential in field theory. We have the fields, electric field, magnetic fields, and those are representative of forces. They're not forces, but they carry force information onto a particle. Okay, and what we want to do is we want to take Maxwell's equations, all four of them, and we want to use that information, the information that's embedded in Maxwell's equations. We want to use the information that's embedded in Maxwell's equations to construct potentials, mathematical potentials, that have all that information in them. And we want really two of them. And what we're going to be doing is we're going to be establishing a vector potential. We almost met it last time, and a scalar potential, and we were briefly introduced to that last time, that have the information from Maxwell's equation in. Now, in the same way we go from a force to an energy, we do an integration. And then when we go from an energy back to a force, we do a differentiation. And so when we integrate, we add in the beginning of our integral, the constant of integration. So there's an extra degree of freedom when we talk about the potentials. We could have several different basis sets, several different ground levels, several different establishments of what the initial condition is. But it doesn't matter, because if we're looking at forces, when we take the derivative, if that constant of integration goes away. So there's a degree of freedom that we have when we're working with potentials that makes our life easier. And it's important to remember that it doesn't matter. It's non-physical. And so the same, we could have two potentials, and by the time we take a derivative to get back to the forces, they'll be the same forces. Now, in the olden days, it was really clear the connection between a measurement and a force. In the old days, there was especially in electromagnetics, there was a one-to-one relationship between a force and a measurement, because you were looking at ammeters and voltmeters that had a galvanometer in it. It had a needle that moved across. Some of you, if you stay up and see old movies, you'll see a needle actually move. That's a representation of some force that's been applied to the armature of that needle to swing it from low to high. That's lost in a lot of the current, a lot of the current generation of instrumentation, because it's all LEDs. They'll mimic that with a liquid crystal display. But in the old world, when people came up with potentials, the connection of what was physically measurable was a force, and you were reminded of that every time you tapped the dial of your voltmeter to loosen up the needle, so that you could make the measurement. Okay. So keep that in mind. Keep that extra degree of freedom in mind. We will need it horribly soon, and we will need it greatly. We will have a mess that we will have to clean up. But let's go review it a little bit and see how we were doing, right? We had four Maxwell's equations. That's floating back here a little bit. Four Maxwell's equations. That's the information that we want to absorb into our potentials. The first thing we did was we said, okay, there's a vector identity. The divergence of the curl of any vector, A, was always equal to 0. And we know that the divergence of B is equal to 0. So if I say B is equal to the curl of A, and I use that to define the magnetic vector potential, one of our two potentials that we're going after, then I introduce an A with all the degrees of freedom in there, and I always satisfy one of Maxwell's 4 equations. So I get, by defining it this way, I satisfy, I get what I need from one of Maxwell's equations without spending any degree of freedom. Okay? And that's a win. That's a win. I can play the same trick with a different vector identity, that the curl of the gradient of phi, a scalar field, is always equal to 0. So I fish around and I say, well, here's one of Maxwell's equations. The curl of E is equal to del B del T. And this isn't quite as simple, but at least I know how to go from B to one of my potentials. So I put in the curl. And then it turns out, oh, okay, well, I've got a curl on one side, I've got a curl on the other side. I'll collect all the terms under that curl. So now if I compare this equation with this equation, I can say, well, gee, if I define E and del by del T of A as the gradient of phi, then I can satisfy this Maxwell's equations, a second Maxwell's equations, without doing anything, just on the basis of a vector identity. No physics, just math. There's no physical constraints. Just, yep, always happens. I rearrange, and now I have one equation that if I know A, I get B. That's good news. Another equation that if I know A and I know phi, a hop, skip, and a jump of a derivative, and I get E. Okay. So in both of these cases, I'm at the potential level, and I take a derivative, and I come back down to a field level. Or I'm at the potential level, and I take a derivative, or I take a derivative here and a derivative here, and I come back down to the field level. Okay? So far things are working out pretty well with respect to establishing a potential. I have 2 new fields, a scalar field phi and a vector field A, and I've got 2 more equations that I want to work with. I've got 2 more equations that I want to mess with. This guy and this guy. So I have to take a look and I have to say, okay, how can I write my D's as a E, and how can I write my H as a B, so that I can substitute in for A and for phi, and absorb the information in this Maxwell's equation and this Maxwell's equation to help me actually get what phi and A are, so that I can work with them. And that's our job today. We're more or less halfway through the structure. So, in no particular order, I'll start with that one there. And I will consider very simple material, so that I'll consider D is equal to epsilon E. And so I'll have the divergence of epsilon E is equal to rho. And if epsilon is a constant, then I can pull epsilon through the derivative. And if epsilon is well behaved, and we know it to be, then I can have divergence of E is equal to rho upon epsilon. Now I want to rewrite this equation in terms of the potentials. And the 2 potentials that I have is A and phi. So I know that my electric field can be written as minus the gradient of phi minus del A del T. What was that? Minus the gradient of phi minus del A del T. Okay? That's what we found last time. So this equation here and I can rearrange this just a little bit. I think that should still be a positive sign, but now now it becomes a negative sign. And that equation is nothing to write home about, but it is what it is. So I'll go ahead and box it up and say, okay, great. Okay. Now I've got one other Maxwell's equations. And that's this guy here, the curl of H minus del D del T plus J. And I've already said that D is equal to epsilon E. And if I do that, then I might as well have a magnetically simple material. B is equal to mu H. So I will have the curl of 1 over mu times B, but I'm going to go ahead and write that as the curl of A, kind of skipping some steps. So if you're nervous about that, leave some space in your notebook and fill it in tonight before you forget. So I'm taking this guy here and I'm putting it into here. And then whenever I see a B, I'm going to say B is equal to the curl of A. And that's where I get that guy from. I'll leave the J alone. And then I'll have plus del by del T of epsilon E. But E, I know, is minus the grad of phi minus del by del T of A. And again, I've skipped a step. So leave a line in your notebook and fill that in later. It'll really help you it'll help you learn it if you do so. I can pull this guy out of that curl. I can pull this guy on the other side of that. I have the curl of A. And I'll have my forcing term on the right-hand side. Now, do you remember the curl of A can be written as the gradient of the divergence of A minus the Laplacian of the vector A? That doesn't get us very far. Can you see that? It's a beautiful thing. Just really, really, really attractive. Nice, neat, easy to remember. And so I have that equation, and I've got that boxed equation. And I got to figure out what to do with them. Okay? Got to figure out what to do with them. Now, let's be a little judgmental here. Let's look for the beauty in this equation. Let's look for what we like and what we don't like. Starting from the left to the right to the left. Notice that I've put the current distribution as a forcing term. And I've talked a little bit about that before. I like that. I mean, I've argued to you that if you go back to Maxwell's equations, charge and moving charges are the forcing terms that beget or give rise to the field quantities E, D, B, and H. So it's only fair that if I have an antenna in the problem, that antenna is still an antenna. It's still a forcing term. Okay? And if I keep going, I've got some terms that kind of look okay. A second derivative with respect to time, and a second derivative with respect to space. I've mentioned before, and I'll mention now, that the name of the course is Fields and Waves, and a wave equation for a field has a second derivative with space and a second derivative with time. So it seems like I have a forcing term in a wave equation that gives rise to the magnetic vector potential A. So that's pretty good. I mean, so far, I like this guy, I like this guy, I like this guy. Okay? I don't mind this guy per se, except it's kind of annoying to have a phi in a term that's A, that dominates by A. I mean, that's a coupling term, and I can deal with that. But what it means is I have to solve a little bit of the phi equation. I have to solve a little bit of the A equation. I have to solve a little bit of the phi equation. I've got to run back and forth, back and forth, back and forth to the equations. It's just annoying. It's just not fun. Okay? Then I have this equation, this term here. What can we say about the gradient of the divergence of A? This is a test of how many people actually did the algebra that I wanted you guys to do. Some of you are looking very sheepish. Some of you are looking away, avoiding eye contact. But this guy's a mess. Right? That's the technical term of art for that term. It's a mess. And what I tell you, we had to do everything in our power to get rid of that mess. All those cross terms. They were all the cross terms in the curl equation. Okay? The D2AZ del x del y. Yuck! These are nice second derivative terms. This could be written as a sum of three nice clean Laplacians of scalars. This is where all the other junk, messy, messy, messy stuff goes. So, it looks like I can do something here. Now, I had 4 equations. I introduced 2 new field quantities, phi and A. And I've used up all 4 of Maxwell's equations. But I still have one more degree of freedom. And that's that $20 bill that I stuck in the back pocket last time. The constant of integration. Taking the derivative of a potential gets me a force. I can observe a force. I can't observe a potential. I can have 2 potential energies that mean the same thing. Remember MGH? What is my height? Is it the height from the desk? Is it the height from the floor? Is it the height from sea level? Doesn't matter, because the ball will drop based only on the change in the potential energy. Okay? So I'm going to use that. I'm going to use that extra degree of freedom, and I'm going to use it to cancel that term. Okay? I'm going to use it to set the messy stuff equal to the minus of that time derivative. Look what happens. If I set that equal to that, then I have a really nice equation here. But the divergence of A is now mu epsilon del phi del t. And this decouples this equation as well. The forcing term of the charge is now only a function of a second derivative with respect to phi in space. And if I get rid of this guy and replace it with the d phi dt term, a second derivative with respect to time. That's pretty cool. So I've just spent my $20. And I think I spent it really wisely. I think I spent it really wisely, because what I have and these really are the 2 equations that we want to box. Now, those of you who are really troubled by the spending of this degree of freedom, you will take great solace in the fact that I can name this. That condition is formally called the Lorentz Gauge. So about half of you will now be breathing a sigh of relief. You still don't understand why we're able to decouple the equations, but at least we have a formal name for it, and I can blame Lorentz for it. I'll do better than that in a little bit, don't worry. But it's such a great opportunity for cynicism that I can't, or sarcasm, that I can't pass it up. Sorry. So we basically are using our adjustment, constant of integration, to simplify our life. And it turns out that if I solve this equation and this equation, I don't have to worry about this equation. But this equation will be true, and so if I solve one of these equations, then I can also use this guy here to get the last equation. Okay? In other words, if I solve for what A is from this equation here, I can take the gradient of it, do a quick integration over time, and I'll get phi. So this is correct and useful if it makes your calculations go that much faster. Okay? Now before we get more comfortable with the before we get more comfortable with the that gauge, let's take a little bit of time to just look at the structure of the two equations that we've gotten. And there's a beautiful parallel, through these two equations. One's for the vector potential, A, and the other's for the scalar potential, phi. So one's a vector equation, the other's a scalar equation. Okay? On the right-hand side is moving charge, current. That's the forcing term for the vector potential A. And the right-hand side is static charge, rho. That is the forcing term for phi. The left-hand side, second derivative with respect to space, balanced by a second derivative with respect to time. And so we call that a wave equation. It's just a consequence of the mathematics that we will see later on when we solve one of these for real, that these will give rise to sines and cosines which look a lot like the waves of a rippling on a still pond, or I guess a swimming pool would be more common. Okay. Now let's take a look at this constant here. Forcing term, second order partial differential equation, forced, linear, with constant coefficients. Mu and epsilon are just numbers. Epsilon is 8.8 times 10 to the minus 12 meters per second. Farads per meter. Silly me. That's a little bit of a slip of the tongue. Farads per meter. So 8 or 9 picofarads per meter. And mu is 4 pi times 10 to the minus 7 henries per meter. So I've got my capacitance and my inductance together as a constant. Okay, so it's like an L times a C, except it's per meters. Each one is per meters. Well, now let's take a quick look at this quantity here. And it is units of whatever A is, which we could figure out. But it has units of whatever A is. And it's divided by seconds squared. So this guy here is whatever the units of phi or A is per second squared. This guy here is whatever the units of phi or A is divided by what? And I've got to add this guy here to this term here. So what units must this constant have? It has to have seconds squared per meter squared, so that these guys cancel, so that I'll have whatever unit A is or phi is divided by meter squared to balance whatever unit A or phi is divided by meter squared. So this guy here is like a 1 over a velocity squared, has units of epsilon and mu. And so if you ask if we indeed have waves, how fast are these waves moving? And it's moving at 1 over the square root of epsilon mu. So c squared is equal to 1 over mu epsilon, or c is equal to 1 over the square root of mu times epsilon. And if you take 8.8 times 10 to the minus 12 and multiply it by 4 pi times 10 to the minus 7, and you take the square root of it, and you take 1 over that, you get 3 times 10 to the 8 meters per second, which we've all memorized to be the speed of light. Right?
So this mu and this epsilon, that's not what the relative permeability and...
Oh, sorry. There we go. Special case of mu and epsilon.
The other ones do, right? The other ones in the box equation.
All right, so it comes from these guys here, right?
Right.
If I'm in free space, that'll be a hard and fast mu naught, epsilon naught, and a hard and fast mu naught. If I'm in a material, it's a mu and an epsilon. So these equations are perfectly valid for either in a material or not. If I happen to take in free space, then I will plug in mu naught and epsilon naught, and I get exactly C. If I keep it as mu as epsilon, I'll get a slightly different velocity. Okay. So 3 times 10 to the 8 meters per second, something that I find much more intuitive to think about, is a foot a nanosecond. So light moves a foot in a nanosecond. And I like that because this is about how long a foot is. And a nanosecond is a very, very, very common time. If you have a cell phone and it's working at a gigahertz, the period of those signals is a nanosecond. And that's about how big the wavelength is. That's about how far the light travels in about that distance. Okay, so a foot, a gigahertz, a nanosecond, a gigahertz, a foot. That's kind of a real nice entry point into electromagnetics. Because otherwise, you're looking at 3 times 10 to the 8 meters per second, and I don't even know how many megameters 10 to the 8 meters is, right? It's 300 megameters, something like that. And that only gets you a second. It tells you how fast the speed of light is, blazingly fast. But for an electrical engineer or an RF engineer, a foot, a gigahertz, a nanosecond. Real nice. Okay. So we'll play around with these. We'll play around with these equations a lot, in fact, over the course of the semester. I'm going to play around with this guy here a little bit and mess around a little bit with it for you. This guy here is going to come out tremendously when we do antennas at the end of the course. So when we do antennas at the end of the course, what we'll do to solve an antenna problem is we will start with this equation here. The J will be the shape of the current in time and space of the current distribution. Okay, so it'll be one thing if I have a little dish antenna. It'll be another thing if I have a straight wire antenna. It'll be another thing if I have a horn antenna. So that's going to be what J is. And so by then we'll learn enough to be able to solve this equation subject to a J. So this equation will let us go from the antenna to the potential, vector potential A. If you're with me, we'll go from A to B. Okay? If we have B, we have H by just multiplying through by mu or mu naught. We've got a couple of choices, but if we have B, we can come up with E. Okay? Or, yeah. So we can plug into that equation and solve for E. And then if we have E and we care, we can get D. But if I have E and H, I can get S. Our friend the Poynting vector, which is watts per meter. So the antenna problem will be J to A to B and H to E and D to S. Okay? That's the roadmap. That's the roadmap that we will use to solve antenna problems. So that's why that's a really, really nice equation. Really, really important equation. Okay. This is also useful, and I'll get to that in a second. These equations are called, depending on where you're from in the world, D'Alembert's equations or D'Alembert's equations, from the French mathematician or the French physicist who first derived these wave equations. So these are our first examples of taking Maxwell's equations and turning them into wave equations. Okay? And it's all predicated on simple substitution, keeping track of your degrees of freedom, and applying the degrees of freedom fairly fearlessly, decoupling those equations. Okay, and that is a really tricky step. Okay, so let me talk a little about that. Let me talk a little bit more about that step. So I called it a gauge. It's an old-fashioned term. And it's really just sort of how you calibrate your gauge, where you're gauging your height from, where you're gauging your height from in your MGH analogy that I was talking about. And remember, B is what kicks the electron around. It's the force that accelerates the electron, QV cross B. So if I can get the same force for two different A's, then I don't care that those A's are different, because the electron sure doesn't. If I have a little electron and I put it on a string and I kick it with the B field that's produced by one A, and I have a different A and it gives me the same kick, the electron doesn't care. It's been slapped exactly the same manner for two different A's. So the physical manifestation, what we measure, is independent or invariant to the difference between those two gauges. Remember, it's like a constant of integration. So suppose I have an A that gives rise to a B, which gives rise to a force. Okay? Now suppose I have a new A, a new vector potential, and it's equal to the old A plus some offset. And I'm writing that offset not as a constant, but even more generally than a constant, I'm writing it as a gradient of a scalar field lambda. Okay, so it's not even, so I'm even more general than just that constant of integration, because this is a whole new gradient, a whole new field. So that gives me a lot of, it's not just A plus or minus a few extra points. I can actually warp the terrain of what that A is in this manner, as long as I can describe that warping as the gradient of a new field. So now B prime is equal to the curl of A prime, and that's equal to the curl of A plus the gradient of lambda, which is equal to the curl of A plus the curl of the gradient of lambda. And what's the curl of the gradient of any scalar field? So B prime that I calculate from A prime is exactly the same as B, and so I've got some degree of freedom in there, and that's what we mean by being able to set the right gauge in just the manner, the right field in just the right manner to be able to cancel that. Okay. All right, I'm going to play around with this equation here, because I think you guys are going to need it next week. Okay? So, del squared, I'm going to write it as V, because I know that half of you learned this as phi and half of you learned it as V. So I'll just switch gears a little bit. So there's my Lambert's equation for the voltage as a function of, say, x, y, z, and t. And it's kind of funny to talk about voltages with the wave equation. Generally speaking, you've talked about fields and A's. So oftentimes V goes with statics. So things don't change as a function of time. So del squared of V is equal to minus rho upon epsilon. And I bet you've played with that equation. Some of you have played with that equation before. It's sometimes called Poisson's equation. Okay. So if I have a charge distribution, this is the voltage responsive to that charge distribution. Sometimes if you have symmetry, you can integrate both sides. And you can find for what V is as a function of space, subject to this forcing term. Okay? How many of you played with that in some other class? Not so much. Interesting. Okay. If charge free, no charge, then this becomes unforced. And that's called Laplace's equation. So what you generally do is you generally solve Laplace's equation subject to boundary conditions. And by the way, this general equation, del squared of a scalar field equals 0, comes up again and again in a variety of all kinds of fields, all kinds of subjects. Thermodynamics, fluid mechanics, and so on. Okay? So this is a very common, applied mathematicians love this equation because it comes up in so many different fields. So you learn to solve it in one field, and you can apply it to a bunch of others. Okay? All right. Now I want to look at this a little bit in a little different way. I want to look at it a little different way, and I'm going to just for simplicity, just for sketching. I'm just going to consider 2 dimensions. You can write the del 2v del z squared. And in fact, everything I do after this, you can just add that term right in. But it'll just save me a little bit of writing. So now what I'm going to do is I'm going to say, supposing I have a voltage at x and y, and I'm interested in what that voltage is a little bit away from it. Okay? So I'm going to write I'm going to say, what is v of x plus h, comma y? And I'm going to write this as a Taylor series. So it's going to equal whatever the voltage is at x and y, so this is a Taylor series. So I'm just expanding this expression in terms of a constant term, a first derivative term, a second derivative term, and if I want to, I can keep going to third, fourth, and fifth derivatives, higher and higher, polynomials. Okay? And that was so much fun. That I'll do the same at minus h. So I go a little bit to the right, I go a little bit to the left, and I have a Taylor series expansion in both directions. If I add these two together, these guys cancel. And let's see, I'll solve for this term here. And I have that. So add these guys together, I get twice of these. Add these guys together, I get an h squared of this one plus an h squared. Divide through by h squared and solve for del 2v del x squared, and I get these two terms popping in there as well. And it doesn't take a huge leap of logic. To do the same for y. Yeah. Well, let's see. These guys are positive. These terms are positive. These terms have opposite signs. These terms are positive. So I'm keeping the equal sign the same. Oh, wait a minute. Minus sign there and minus sign there. Excellent. Good job. Sorry about that. Yeah, that's good. That would cause me some problems later on. Okay? Now, I could do this in a third dimension just as easily, but it's just kind of too much bookkeeping. So now, if you remember your Laplace's equation, del squared del 2v del x squared plus del 2v del y squared is equal to 0. So if I add these guys together, the left-hand side goes to 0. So if I take the right-hand side, and I add these together, I've got minus 4 v of x and y, and I've got this term, this term, this term, and this term all equals to the same 0. Sorry about that. Now if I draw this, I have v of xy and I have 4 spots just a little bit away from it by a distance h. So Laplace's equation tells us, this is a huge leap, that the voltage there is the average of its 4 nearest neighbors. So the voltage at this point here is the voltage of this point, this point, this point, and this point divided by 4. And that's a simple numerical average, right? So if I extend this to this third dimension, then this goes to a 1/6 because I'll have 3 of these terms, and so it'll be the average, above the page and below the page by some amount h. Okay. So to me, this is absolutely huge. It does a couple of things. One is it gives you a little algorithm, a numerical algorithm, for solving del squared v equals 0. Okay? And in past classes, I've assigned that as a computer project. Okay? But the other thing it does for me is it begins to give me, and I'm not going to be that authoritative with you guys, because there's a few little chinks in this logic. It's not ironed out 100% perfectly. But to me, it suggests a physical interpretation for the del squared operator. And that is that the del squared operator is an averaging operator. It's a low-pass filter. Okay? It smooths out irregularities as opposed to accentuating the regularities. Right? It's the same argument I say that if I take the height of all of you in the class, if I add my height to your heights, and then divide by the number of people we are, that is the average height of the class. Okay? So that's all this is doing, is it's smoothing out the differences in the voltage, just in the same way that I'm accentuating what's the same about our heights as opposed to what's the difference in our heights. Okay? If I wanted to say how much shorter I am than anyone else, I would pick one of you and I would subtract my height from yours, and that extra 6 inches would be the difference. It would accentuate the difference. So you use sums to smooth, and you do differences to do differences. Okay? So when I go back to these equations, these wave equations, I see the del squared operator, and I say that as these propagate, the differences will iron themselves out in some slow, repetitive algorithm that nature follows in solving the stepping of the wave equation. Let me put it to you this way. If you look at the lights on the ceiling have a very complicated distribution. Light fixture, space, light fixture, space, light fixture, space, light fixture, space. And yet when you look down at the floor and you look down at your desks, pretty evenly lit, right? You don't have perfect dark shadows underneath where the light bulbs aren't. And I would argue, I'd submit to you that that's a consequence of the del squared operator. The del squared operator is ironing out and filling in the gaps between the lights. And if you remember, even for the old-fashioned light bulbs, you didn't really see the shape of the filament very well, did you? It just blurred out into a nice beam of light. That's kind of what you want. Unless you're doing a projector display like we have in the class, and then you have to work hard to transfer the image. These equations are written on a little spatial light modulator in there, and you have a projector lens that projects that difference onto the screen. So that the job of the lens is to fight this averaging. Okay? So I find now, and again, I took a huge leap of logical faith. Okay? It's not as clean and nice, but I like it. I mean, I used the consequence of this guy here, and no other term, no time derivative term, to come up with that averaging analogy. But it seems to hold pretty well physically as well. And so for that, I offer that as my final interpretation of these del squared operator. We talked about what a gradient might be. Remember the canteen of water and the steepest slope? We talked about divergence, which is a flux of a quantity, particularly evident through the divergence theorem. We talked about the curl, which looks for vorticities. We talked about that in terms of tornadoes and how you would look for those kinds of effects. And now the del squared operator, I offer the interpretation as an averaging, a low-pass filter, or an averaging operator. Okay? All right. Let's see. 15 minutes, right? How do I want to spend those 15 minutes? Let's see. I'll give you a choice. Do you want to hear more on gauges? Or do you want to go on to materials?
I say gauges.
Gauges? Anybody?
Gauges.
Okay. All right. Is that because you think you're finally going to understand it after I get through with this?
Yeah.
Oh, sorry. You fell into the classic trap. But I'll give you another example of a gauge. I think that'll, at least through familiarity, you'll get more comfortable with them. So let's see, where were we? We had del squared phi, I think I was using, plus del by del t, the divergence of A is equal to minus rho over epsilon. And then the other equation was the gradient of the divergence of A. Boo hiss on that term, it's ugly and messy. All the cross terms.
Can you move?
Oh, absolutely, I'm so sorry. Thanks for telling me that. So one nice thing about going through this again is we've talked a lot about these terms, and now they're a little bit more familiar to you. You know the role of these guys here, and you've been reminded how ugly that guy is, and you see the coupling term here, and now you can see the coupling term there as well. Okay. Now the small change I want to make on these is we did two material relations. We did one for the capacitance per meter and one for the inductance per meter. I'm sorry, one for epsilon and one for mu. Okay, and now I want to take into account the conductivity of J. Okay, so suppose J is equal to sigma E. And what that means is that J is equal to sigma ugly. J is equal to sigma times minus the gradient of phi minus del A del T. I'm just substituting in from Maxwell's equations what E is in terms of phi and A. You see that? Where I got that? Don't be afraid to say no. You're unconvincing. Using the second step, I was able to get phi in terms of A and E. And then I rearranged it so that E was equal to the minus del V minus del A del T. Okay? So now I can substitute this in. And this term gets changed just a little bit. And these two terms get a third one. To look like that. So if I put an Ohm's law into this, I've got this guy going on, and then I've got not two terms, but I've got a first derivative term. It's neither here nor there. And so what I'll do is I'll change my gauge so that now that equals 0. And so the divergence of A goes into there. So this equation becomes decoupled with 1, 2, 3 terms in it. And this equation becomes decoupled with 1, 2, 3 terms in it. So a little bit harder than what we had before. So now we have a second derivative in space, a second derivative in time. Oh, sorry, I guess technically I didn't get rid of my charge. And then I also have a first derivative with respect to time. And every time you see a first derivative with respect to time, you think about Stokes' law of drag. It's always a loss term. In either of these equations. And we know that, right? Because it's got a conductivity in it. It's got a resistor in there. And so this acts like having an inductor, a capacitor, and a loss term or a resistor in there. So again, it's not unreasonable, particularly in this equation here, the equation for the voltage. It's absolutely not unreasonable to think about that as a lump circuit capacitor, a lump circuit inductor, and a resistor, LRC, so that that voltage is changing as a function of time, moving between the inductor and the capacitor, to the inductor to the capacitor, to the inductor to the capacitor. That's your oscillation. And every time it slides across the resistor, there's a tax paid in heat. A little bit of energy moves out of the electromagnetic system. Just as we learned in Poynting's theorem from last time. Okay? So all very, very, very consistent. All very consistent. We have the capacitance, which is the potential energy. We have the inductance, which is the kinetic energy. The wave is formed by the trade-off between potential, kinetic, potential, kinetic, potential, kinetic. When I include the loss in there, I have a sinusoid that now gets decayed exponentially. Okay?